Hello everyone. I welcome you all to the e-video prepared for unanimous syllabus under the Regulation 2021. Today we are going to see the session on the topic Inter-Process Communication, that is IPC and Scheduling Criteria. From the second unit, Process Management, in the course CS 3451, Introduction to Operating System. Myself, Dr. C. Rani. Let us see the objective of today's session is to know about the inter-process communication and the scheduling criteria. The session outcome, the students may be able to understand the inter-process communication and the scheduling criteria. Here is the outline of today's session. First, we'll be seeing about what is meant by inter-process communication and what are the types of processes available and what is the need of inter-process communication. And next, we'll be seeing about the two fundamental models of inter-process communication. There are two models. That is, first one is shared memory model. Second one is message passing model. And next, we'll be discussing about the properties of scheduling algorithms, otherwise called as scheduling criteria. There are 5 properties over there. The first one is CPU utilization, throughput, turnaround time, waiting time, response time. So the types of processes, there are 2 types. So whenever the process executes concurrently in the operating system, the process may be of 2 types. One is independent process, the other one is cooperative process. So what is meant by independent process? That is, if the process that cannot affect or cannot be affected by other processes executing in the system. In other words, any process that does not share any data with the other process is called as independent process. The next is cooperative process. That is, if the process can affect the other process executing the system or can be affected by other processes executing the system. And also, any process that shares the data with other processes is called as cooperative process. So what is the need to have the inter-process communication? There are several reasons for providing the inter-process communication. The first one is information sharing. Since several users may be interested in sharing the same piece of information, we need to provide an environment to allow the concurrent access to such information which is shared. The second one is computation speed. If you want a particular task need to be done, that is, if you want a big program need to run in a faster manner, then we can go on breaking up the long program into subtasks, and each subtask need to be executed in parallel with other process, which is called as multiprocessing. So if you are carrying out the multiprocessing, we can increase the speed, computational speed. For that, we need a inter-process communication. The next one is modularity. If you want to construct the system in a modular fashion by dividing the system functions into separate processes or threads. Convenience. The next is convenient. Even an individual user may work on many tasks at the same time. For example, the user may be editing, listening to the music, or they may compile the program in parallel. For all these 3 tasks need to be done parallelly, we need inter-process communication. There are 2 fundamental models of inter-process communication. They are shared memory model and message passing model. So the cooperating processes require an IPC mechanism that will allow the process to exchange the data and information. So in the shared memory model, the region of memory is shared by the cooperating process is established. The process can then exchange information by reading and writing the data to the shared region. In the message passing model, the communication takes place by means of exchanging the messages between the cooperative processes. So first we'll see about message passing model, which is useful for exchanging the smaller amounts of data because no conflicts will occur or conflicts will be avoided. So message passing is an easier task to implement in a distributed system than a shared memory system. So this message passing systems are implemented using the system calls and thus require the more time-consuming task of kernel intervention. Here you can see the how the message passing model works. Here there are two processes, process A and process B. If the process A needs to share the data to the process B or exchange the data from process A to B, first the process A will share data to the kernel, wherein which a message queue is maintained, where the messages are stored in the message queue. So whenever it is needed from the kernel only, the information will be passed on to the process B. So this what happens in the message passing model, wherein which a smaller amounts of data will be exchanged from one process to another process with the help of the time-consuming task of kernel intervention. So kernel is a space wherein which some piece of messages will be stored in the message queue. Afterwards, it is then transferred to the process B. The next model is shared memory model. Inter-process communication using the shared memory requires the communicating process to establish a region of shared memory. So a shared memory region resides in the address space. So it requires some amount of space, memory space, address space of the process creating the shared memory segment. So other process that wish to communicate using the shared memory segment must attach it to their address space. Then the information can be exchanged by reading and writing the data in the shared region. So the form of data and the location are determined by the processes and are not under the operating system's control. So these processes, the processes are also responsible for ensuring that they are not writing to the same location simultaneously. So here you can see this picture. If the process A wants to share some data to process B, so what are the informations need to be shared will be stored in the shared memory space. So process B can access the data from the shared memory region. Next, we'll be seeing about what are the properties of scheduling algorithms or otherwise called as scheduling criteria. There are 5 properties are there. The first one is CPU utilization, throughput, turnaround time, waiting time, and response time. First, we'll see about the first property, that is CPU utilization. So this scheduling criteria is also called as scheduling methodology. Different CPU scheduling algorithms have different properties. We'll see about these 5 properties. CPU utilization means the process which keeps the CPU as busy as possible. So the CPU will be never kept idle by scheduling more number of processes continuously. thereby increasing or maximizing the CPU utilization. So the CPU utilization can range from 0% to 100%. In practice, it can also range from 40 to 90%. Next property is throughput, which is defined as the rate at which processes are completed per unit of time. That is, number of processes executed by the CPU per unit of time. It is called as throughput. So for long processes, the throughput rate may be 1 process per hour. For short transaction, the throughput may be 10 processes per second. The next property is turnaround time. It is defined as how long the processor takes to execute a process. It is calculated as the time gap between the submission of a process and its completion. So it is calculated using the formula, the difference between the finish time and the arrival time in milliseconds. The next property is response time. Is different from that of the turnaround time. Response time is defined as the time taken to start responding from the submission time. It is calculated as the amount of time taken to start responding and not the time it takes to output the response. So response time is also called as, or otherwise called as, start time. It is not based upon the time taken to output the response. So it is calculated based upon the time taken to start response. So it is called as start time. Next property is waiting time. It is the sum of time period spent in waiting in the ready queue. So waiting time is calculated from the difference of start time and the difference between the start time and the arrival time. Next, we can optimize. We can use the optimized scheduling algorithm by following criteria need to be satisfied. That is by maximizing the CPU utilization, maximizing the throughput, and minimizing the turnaround time, waiting time, and response time. So here in this figure, you can see the two types of ready queues are maintained in the scheduling algorithm. In order to have an optimized scheduling algorithm, we need to focus on these criteria to be satisfied. In this diagram, you might be coming across or focusing on the ready queue and the waiting queues. So whenever the process is in the ready to execute, will be placed in the ready queue. So here the number of processes will be waiting for the processor to be assigned. When the processor is being assigned, it starts executing. It moves from ready state to running state. So in the running state, the process will be start executing its instructions. Okay. So from the running state, it can move to the waiting queues. That is, it moves to the waiting state whenever there is IO request occurs or any interrupt occurs. It moves from the running state to the waiting state. From the waiting state, it again moves to the ready state and again goes to the running state. It goes on, the cycle goes on. After all its instruction has been executed completely, then it moves to the terminated state. So these are the references used for preparing the slides. Thanks for watching. Thank you.